Hello, hi all, good afternoon, everyone. So myself, I'm Deepti. I'm talking on behalf of Anoop Divakaran, who is out for a meeting actually. So I'll be taking over as a host in this webinar. So from my end, so basically I take care of the southern region, all the sales and operations part. So I have Ashutosh along with me who will be taking care of the solutionings of the FPGA. So before I start, I have more attendees who would be joining. So probably within 5 minutes we can probably start with the technical session. So I will just provide a short brief on what Digito Technologies is and what are the main solutions that we offer. So I have a short presentation with me, which I'll be sharing with you on the screen. Yes, so Digito Technologies, like our company has been established in 2018, and we are based out of Bangalore, and we basically deal with academics and research institutes providing solutions in terms of test and measurement, industrial automation, and wireless technologies, as well as robotics and FPGAs. And we are actually partnered with few prominent OEMs like ST Microelectronics, Digilent, Q Tools, and Qbrate. So this is our new collaboration wherein we are providing solutions for quantum as well, and we are collaborated with Advantech and TMY Tech and Mantis Wave for wireless solutions and Crowbot for robotics technologies. So these are the prominent OEMs wherein we work with, and the our main focus lies on the test and measurement, AI and machine learning, VLSI design, wireless and quantum solutioning. So that is a short brief regarding us. So I have the Digitode sales ID and the contact which is being presented on the screen, wherein you can reach out to us for any kind of solutions in terms of any support regarding the technologies which we offer, and our technical team and the sales team would be reaching out to you for providing all kind of supports. So I'm not making so before we start with the session of Ashutosh, like I just wanted to give you a short information that if in case you have any queries, you can probably put it across on the chat window. So Ashutosh would be able to address those towards the end of the session. So I think I'll hand it over the session to Ashutosh for him to present on the FPGA part. Ashutosh, you can start your presentation.
Hello everyone, my name is Ashutosh Tiwari and I'm an FPGA design engineer at Digito Technologies, and I'm here to give you a brief explanation on implementation of deep neural network on ZedBoard. So deep neural network is basically performed on the pixel values. What we have, covered the previous session on OV7670 camera module to VGA pipeline. So the previous network what we have discussed till now was a convolution based operation. On this webinar, we are going to discuss on ZedBoard and what are the other features of ZedBoard. So before starting with the deep neural network, I'm just going to give you the brief explanation of ZedBoard and the main peripheral components that are present on ZedBoard. So this is the power supply which it requires. It requires a 12 volt of power supply and 3 ampere of current to run this FPGA. We also have a PMOD section where a general purpose input output is used to compute the high efficiency parameters. So along with that, we also have an OLED OLED and user buttons we have. This is the FMC part of ZedBoard where we are using it for SDR operations and gigabit Ethernet. You can use it as an expansion module on our ZedBoard. Along with that, this is the JTAG header, what we have used. This is the JTAG. You can program it through the JTAG part. This is the VGA cable, which is giving you 4-bit per component output. So this VGA has practically 14 signals, 4-bit per component. So red has 4 component, blue has 4 component, and green has 4 component. Along with that, it has 2 synchronization signal, which is called as horizontal synchronization and vertical synchronization. This is a audio codec which is present in our ZedBoard, which is giving you the line input to a headphone output. So ZedBoard is practically a bridge or a loopback can be implemented through this audio codec. We have a gigabit Ethernet, which is called as RJ445 Ethernet magnetics. This RJ45 magnetics is used to implement many protocols like TCP protocol, UDP protocol, and other frame transmissions. So focusing on the VGA part, this is the screen display, what you will see in the demo. So the screen display has total of 640 into 480p resolution. So in order to get 640 into 480p resolution, you have a total line of 800 pixel address and 525 of line address. So this is the total 800 of pixel address. And this is the 525 line address, which is required to generate a fixed output. So as we have a active region of 640 and a vertical line of 480, we are using a refresh rate of 60 hertz. So for 60 hertz, the calculation, we are using 25 megahertz as our pixel clock. So how am I implementing a deep neural network? We have discussed the camera capturing on the previous webinar. So this time we will focusing on how you can implement AI on those captured pixels. So to capture the pixels, first you have to understand the data flow of how an input which is given to this is resized and how it is predicting a digital value. So a neuron, how you design a neuron is based on a very basic formula. So the for every input value what we are giving, there has to be a weighted value for every neuron, and there should be an activation function and a bias value. So we can use a lot of activation functions like ReLU, sigmoid. It will be discussed on further slides. So how can you train your pixels in a way that it is going to give you a predicted output? The FPGA has to predict an output on its own behalf. You have to train the FPGA, or you have to use certain libraries or certain functions to create that convolution neural network. So it also, to implement these functions, you have to calculate the weights and the activations and the feed forward propagations. So what is a feed forward propagation? It is resulting to the training loss. For every feed forward operation you try to implement, there should not be any training loss to your device. So once there is an error, it has to scale those values, it has to remove those pixel values, and our neuron has to downsample all this lost data. So once that is completed, you have to apply the weighted difference with the current weight. So for any change in input, there should be the change has to be reflected on the output. So this is how we are trying to resolve the errors from that prediction, and from that training loss, we are trying to get an accuracy in our output. So we are not using a normal neuron, we are using a sigmoid neuron because there is a very big difference between a normal neuron and a sigmoid neuron. So for every input what we are giving here, this is the sigmoid activation function. So the weight 1 to weight 2 till weight n, whatever the values we have, we are giving an output based on this activation function. So this is called as the sigmoid function. So there are 3 types of sigmoid functions which can be used. One is a sigmoid, one is tan hyperbolic, and one is rectified linear unit. So this is the respective graph and the respective formula for these three activation functions. So these three activation functions are implemented in our code. So I'm going to just explain very briefly what is the difference between these three. So a ReLU function, there is a range between 0 to x for every rectified linear unit. But a sigmoid function is also considering the backward or the negative values for the activated values. Tan hyperbolic is using the same function as respected below. So for this formula, this is the respective graph. So the sigmoid function what we are using has a range between 0 and 1, but the tan hyperbolic has a range between 1 to -1. So the tan hyperbolic has the range of 1 to -1. Till that range, it is going to cover. And rectified linear unit will have activation sparsity based on the likelihood of the pixels. For likelihood of the neighboring pixels, it is going to take the maximum of 0 and the input values. So this is the external architecture of a sigmoid neuron. The weighted values what we have implemented in our RTL is used on our data files. We are uploading our weighted values on the data files. And the input values what you are seeing, this is the input what we are trying to give from our pixels. So this is the 12-bit pixel values what we are trying to give from this my input value. So for every 12-bit of pixels and for every weight, it is getting through a multiplier. And once it is going through a multiplier, it is also going to a adder part. So for every closed feedback loop, of the bias what we are using a ALU. So for ALU, it is going to go back to a closed feedback loop. So once the sum for this complete architecture is completed for the bias value what we are giving, we are applying an activation function on the end of this process. So the interface and control logic what we are using in our FPGA is we are using a control logic of BRAM to store all these weighted values and giving the output in a same 12-bit pixel output format. So this is how you can implement a deep neural network by the multiplication and the additional operations. So we are reading it back from our memory. The memory what we have used in our RTL is a BRAM. So in this image, you can see that for every small change in weight or bias can cause the change in output. So if there is a small change in this weight or any small change in this bias, there will be the reflection of that changes has to be reflected in our output. So if we don't find any change and if your weighted values and bias value is correct, so the prediction will be correct from the FPGA. So this is how you are training your FPGA to predict the digital values. So to use a kernel, so kernel is something we have to implement in our image to apply that convolution neural network. So for that, you have to use a larger kernel and a deeper layer has to be implemented. The more larger kernel you use, there has to be the number of layers that are implemented should be more. So for that, for every 10 nodes of 10 different numbers, it is going to give you the 10 outputs. So as we are predicting values from digital values from 0 to 9, it is a total of 10 nodes has to be implemented so that FPGA can be trained to understand 0 to 9 values from its own. So based on that learning data, the data what we are applying on that it can be called as max pooling layer for data dimension. So you are max pooling the layers in such a way that for the prediction has to be completed or the training has to be completed for all the 10 different digits. So this is the basic flow of number classification for in ZedBoard. So The basic architecture is first you have to start. So in our perspective, the start would be the complete capturing of our pixels. The pixel has to be captured completely, and after storage, there shouldn't be any glitch on your output. Once the operation of storage is completed, you are processing your data for training. You're giving the data for the training purpose. So the data is completely split into two different parts. So once the data is processed, you have to select the samples. So in our first slide, I can show you that the two-dimensional convolution operation with the appropriate kernel size, which we have used as 3x3 kernel, we are using the input and output of the channel. So for each neuron, there has to be a weight matrix and a bias value. So as discussed here, you require a different weight value and a different bias value for every single training. So for every neuron and every kernel, you have to use a weight matrix and a bias value to vanish the gradient problems. So for any training loss which will happen in our ZedBoard, there should not be any training loss. There should not be any wrong prediction from your FPGA. So you have to initialize that weight matrix. That is the second part what we are using. So the first part would be the training and the validation process. So once we have completed that batch part, we are using to rectified linear unit as the activation function to extract that feature. So rectified linear unit is the activation function you have to use to extract that feature. So these feature parameters and the feature extraction happens on this particular part. This is the feature extraction part. So here you are implementing rectified linear unit. So the output of the convolution layer has to be flattened to a one dimension, and it has to be forwarded to two fully connected dense layers. So the classification and the outcome of these validation data sets has to be completed. And if the condition is true that yes, the hyper adjustment parameter is satisfied from the training process, it will go to the testing process for our trained data. So this is the path where you are training your data using the activation function and the max polling. And this is where you are testing the data. You are trying to test the accuracy of your training. So the optimization, what you are using in this has to be achieved only if the condition of optimization is true. You are testing that process. Otherwise, there is a training loss in your data and you have to retrain your network. So there is some issue in your code that it is optimization is failed from your end. So this is how a fully connected network is implemented. And again, you have to go through the same process of data pre-processing, because if you have to predict, the same process has to be predicted, and the predicted accuracy should be greater, around greater than 80% in our case. So as explained, the prediction of how we are recognizing, there has to be some probability. At what rate, how are you training this data? For that class probability, you have to implement a cross entropy function. So there is a built-in cross entropy function inside our RTL where you are training, and the recognition ability of your FPGA or the output is more. So for real classifications, there should be an accuracy rate, and the losses has to be calculated separately. So this is the class probability or a cross entropy function which we have implemented in our FPGA. For every simple data, this is the predicted value. For every predicted value, you are receiving a cross probability. So this is how I am validating my RTL, that okay, this my RTL is working accurately because my cross entropy is working fine. So my prediction is based on the data set, and the accuracy and losses are calculated separately. So how are the fonts predicted, and how am I facing these losses? How so You can use a MATLAB for this training part. So I'm have shown how you can implement a fully connected network on your RTL by certain steps. So these are the steps which I will be explaining to you. But how are you implementing the training loss and how are you determining this accuracy? So you can see that the accuracy is starting from 93 and it is ending at 94.8. So you can ask a question that why is my accuracy not 100%? It is not possible to predict any output to 100%. Fully connected network, it is not possible to say that your accuracy is exactly 100%. There will be some glitch, there will be some loss in this data. Maybe the validation is incomplete, the FPGA is not able to predict all these data sets. Are these data fonts? Are the FPGA is finding that there is some neurons where the loss is happening? So this is the graph between the epoch and the loss. So based on this graph, you can say that the predictable output or the accuracy is will be between 93 to 94.8. So the first step of fully connected network is that you have to configure what is the set number of weights, a bias value, and an activation function. What are these three important parameters as shown in my previous value? There are only three inputs which you have to give in your model to give this class probability cross entropy output. So the first will be my weights, what weights I'm including in this, what is the bias value, and what is my activation function. So the internal memory to store these weights, like I explained, was data files or a code dat files, what I have called in my RTL, where I am including my weights in my module. So the bias handling is called as the pre-trained network. You have to train your camera through a software which is called, it can be a Python module, it can be a MATLAB, it can be a TensorFlow, it can be a YOLO module, but the pre-trained network has to be completed only through this. These bias values can only be given through this software. You're using a pre-trained network. You can't train your camera through FPGA. The training is only completed through your Python or MATLAB or any other softwares as mentioned before. So how am I receiving an input? How am I receiving and how am I reading these weights one by one? So this neuron is receiving an input directly from our camera module. So for every input values for this neuron as shown here, we are giving, we are reading this weight from that data files and we are multiplying each with the corresponding stored values or the weights. So this is where I'm accumulating all my bins. You can say that this all my pixel values are getting accumulated and these bins are performing an histogram equalization. So based on this histogram equalization, it can be called as an, another word for histogram equalization is also called as accumulation. So for each input which is multiplied with a weight, the result is prepared for the accumulation. Now the bias value or the value which you have got from that pre-trained network, it has to go through an overflow protection or underflow protection. So once the multiplication is completed, you are using an activation function. This is the activation function because this process is completed till now. You are checking if there is an underflow or overflow. You have received all the weight values and this is the pixel values. Now you have to reach to this activation function, which is called as a rectifier linear unit or sigmod. So for rectified linear unit, there will be only two possible values and an intermediate values between these two, which is called as 0 or the 1. So from 0 to any input values, what it ranges, sigmoid is used to express only the graph between 0 down to 1. I can go back to my graph as shown below and I can just explain it again. So ReLU is only going to take you the values from 0 to 1, whereas the sigmoid is taking the values from this formula. So Once this activation function is applied, you are just getting a valid signal from our FPGA that okay, my training is completed and I'm going to my testing procedure. So once my training and validation process is completed, it has to be optimized in such a way that it has to go to back to the testing process. So this hyper parameter optimization is where it is determining that how how accurate your output is. So if your optimization parameters are not satisfied, you have failed to train your network. So the first part which we will explain is the placeholder and the parameter settings. So the input whatever you are receiving, the prediction we are giving it on a 28 cross 28 matrix. So for every input what you are receiving, the output what the FPGA will give you, that will be on a 28 cross 28 matrix. So in this two-dimensional matrix, the conversion number has to be set to -1, and you are indefinitely matching all the images. So for this 28 cross 28 function, you are using a kernel size of 3 cross 3. So for this 3 cross 3 conversion operation, you are using a batch normalization layer. So this is where your batch is normalized and you are applying the final ReLU activation function for this feature extraction process. So this is the comparison between the sigmoid and the ReLU function. I think it is visible. So the graph between the sigmoid and the ReLU is this. And the resource utilization which we are used, this is the ZedBoard resource utilization. So for DSPs and BRAMs, we have used a lot of BRAMs in this. That's why the BRAM chart is high, because we are storing all our weighted values for this. So after applying this ReLU activation function, there should be a dropout, right? So the discarded 40% of trained neurons to reduce the overfitting. We are still processing this loss. So still I can show you the RTL. Let's start with the RTL part. So this is my ZedBoard top module, which I have used. I have used a clock of 100 megahertz of oscillator, a key input where I am switching my train network for normal grayscale image or color spaced, normal grayscale image and color image. So based on this, I'm even getting an output on my LED, and you can even use it for a 7-segment display. For 7-segment display, you can use it on a Nexi A7 to predict or see the classified output. This is the camera module what we are using. This was discussed on our previous webinar, the OV7670 module, and this is the I2C settings which where you are configuring or capturing your camera images. This is the master clock what we are using, the master clock what we have to give to our FPGA or the camera module, and this is the pixel clock what we are receiving from our module. So the output will be fixed, like I explained, there will be 12-bit components. So 4-bit per component will be RGNB, and my horizontal and vertical synchronization will be explained here. So this is the top model, and this is where my optimization is started. And this is the data files where I am calling all my RAM data, the storage for my optimization process. So you can see that there is a 7-segment output. For every prediction input, whatever I'm receiving, I'm giving a fixed output. So let's go down to the nearest interpolation or the resizing of the image. And why do you have to resize this to a 25 megahertz of pixel output? So the input row column what we are receiving from our camera model is 640 into 480p, but you have to convert this input model to a 32 cross 32 output. So this is where I am resizing my resize write data. So my data is for every input, we are making a nearest interpolation. Bilinear interpolation is completed in this module to give you the output value. So once the optimization part is started from here, like I explained that the training has to be completed. So for every optimization, we have a ReLU function implemented here. This is the ReLU model, what we are using. So for ReLU model, we are even using the max polling architecture. This is where I am using the max polling completely through Verilog without using any IPs. So the storage what we can use is a simple BRAM. You can see that I have implemented a basic BRAM based on the length and the depth. My pixel values are stored based on my FIFO size. So for every pixel counting, what we have done in this, there is an optimization. There is a ReLU function what we have implemented again. So we have called the same module again and again. So the total number of layers what we have implemented in this would be around 15. We have implemented 15 layers of this and we are using a fully connected network. This is where I am connecting my whole poll data in my fully connected network module. So the code is little complex to explain every single parameter, but based on my calling module in my optimization, you can understand that these modules are called and the weights what we are receiving is based on the data files. These data files are called for my convolution core data for continuously updating the weights and the bias value. So for the first layer, what we have implemented till third layer, we are using the different data files. So for fourth layer, I'm again using a different data file. So every single convolution operation which is happening for different layers has gone through a different data file. So based on their calling, we are performing all these operations and the layer output what we are receiving from each single output is going back to the fully connected network. This is where my final output or the D out or the enabling part what you are using. This output is going through all this max polling architecture. So for every activation function, what we have received from this, we are giving a final output. So this is where I'm using a fully connected network. So going back to the displaying part, this is the display part where I have used a horizontal synchronization, vertical synchronization, and front push and back push. So the active region, like I explained that time, was like I have a 640 into 480p of active resolution. I have defined it. And the refresh rate for my screen is 60 hertz. So I'm using a 25 megahertz of pixel clock. So for total 640 into 480p, the total number of pixels per frame would be 3,07,200. So the output part is also completely done on RTL perspective. So for every active functions, what I am receiving from my BRAM, this is the RAM data input what I am receiving, and I'm just classifying this into three different components. So for red component, green component, and blue component. So going back to the top module, I'm going to just explain it in a more simplified way, like how MI CNN is implemented even on the 7-segment display output. So the BRAM output, what we are reading from this BRAM for the BRAM write address and write data, this write data is coming directly from our OV7670 capture module. This is the where I am capturing all my RGB data based on my rising edge of my pixel. And when my rising edge of pixel is completed, I am giving it as my output through the camera module. So for the captured module, what we are receiving from this camera, we are receiving it back to the BRAM. So the BRAM output is going to this VGA output. So the output of this BRAM is also given as an input to this resize module, right? So this is where the output of the camera capture the stream data, what I'm giving from my FPGA, that stream is going back to the resizing of the image. So this is where it is going to the output also, and I am giving it back to my resizing module. So this resize write data is again going back to the convolution operation. So for the optimization of CNN module, the real values what we are using, I have to use a $C-log2 files because you are using the fixed point conversion. There is a difference between a fixed point and floating point. You can't use the floating point in your display or in your RTL. So you have to use a C-log2 function for every input number. So based on that, you have to perform a image convolution operations. So for every sigmoid function and the ReLU functions, what we are going through, we are going to see the module for that. And the optimization of each module, why are we calling for every module? So the input of one module is given to an output of another module. So the out data of one module is input to this part. So the conversion optimization, what is completed there, is going as an input to this ReLU module. So the output of the ReLU model, what we are giving, it is going as an input to the max polling architecture. So this is how I'm connecting the flow, the data flow and the behavior of this module is completed through this particular logic. This is how I'm connecting all my modules from optimization to ReLU function and from ReLU to my max polling architecture. So I'm going to start with my demo. So let us start. So this is where I have used a number. This is the number what I'm using. A number basically what we are using as this value. I'm giving it as an input or giving for my FPGA using this CMOS camera. So the CMOS camera is giving a prediction of 6 here. So this small window what we are seeing, the frame is freezed. So you can just remove this and you can see that the frame is freezed completely, and that trained output, there is the computing time for this is less than 27 microseconds. So for another data what we are receiving, this is the second output. So the classification of any data from 0, 0 to 9, the prediction will be accurate. So for a number such as 5, so you can see this is my number, what I have implemented in this. As soon as my switch input, this is the switch input which I'm giving. Once I'm giving the switch input, my output is predicted and my frame is raised. So for suppose a number as such as 2, the output will be shown. So does anyone have any questions regarding this?
So Ashutosh, are we done with the demo and the presentation?
Yeah, we are done.
Okay, so everyone, thank you for taking the time to join with us, and we hope the information shared today was helpful and insightful. So, if there are any questions or if you require any topics that needs to be repeated by Ashutosh, you can probably raise your hand or you can put it as a questionnaire on the Q&A session box.